Tonight, you're taking a journey through every type of black hole in the universe that no one talks about. And once you see what's been deliberately left out of every documentary and textbook, you'll understand exactly why. From the tiny ones that may have been born in the first heartbeat of the cosmos, to the monsters that sit at the center of galaxies and weigh more than billions of suns. You clicked on this video because you wanted to know what is really out there in the dark places between the stars. And let me tell you, the black holes we think we know are just the beginning. What if the ones hiding in the shadows are stranger than anything we ever imagined? Let that thought settle in for a moment, because tonight we are going on a journey across the entire universe. We are going to visit every known kind of black hole, from the smallest to the largest, from the oldest to the ones being born right now. And by the end, you might look up at the night sky a little differently. You might realize that the darkness between those twinkling stars is not empty at all. Tonight's journey is brought to you by Beyond the Stars, a full collection of overnight cosmic sleep journeys available at mycosmicdrift.com. Link in the description. It is full of invisible giants, silent travelers, and ancient relics from the very birth of everything. So let us begin at the beginning. Not the beginning of this video, but the beginning of everything. The Big Bang. Nearly 14 billion years ago, all of space, all of time, all of energy, and all of matter were compressed into a point smaller than an atom. And then it expanded, rapidly, violently. In a fraction of a second, the universe went from something infinitely small to something unimaginably vast. And during that wild expansion, something strange may have happened. In certain spots, the density of matter was not perfectly even. There were lumps, thick patches of energy crammed together so tightly that they could not spread out fast enough to keep up with the rest of the expanding universe. And those lumps, those tiny dense pockets of matter, may have collapsed under their own gravity right then and there, forming what scientists call primordial black holes. Now, here is the fascinating thing about primordial black holes. They did not form the way other black holes do. They did not come from dying stars or colliding galaxies. They came from the chaos of creation itself. The very first moments of the universe were so extreme, so unbelievably hot and dense, that black holes could form without any star needing to exist at all. Think about that for a second. Before there were any stars, before there were any planets, before there was even light as we know it, there may have already been black holes. Tiny ones. Some of them could have been as small as an atom, but with the mass of a mountain. Others could have been larger, maybe as heavy as our sun, or even heavier. The range was enormous because the conditions in the early universe were so wild and unpredictable. But here is where it gets even more interesting. If some of these primordial black holes were very small, they might not even exist anymore. And the reason for that has to do with one of the most mind-bending ideas in all of physics. It is called Hawking radiation. In 1974, a physicist named Stephen Hawking proposed something that stunned the scientific world. He said that black holes are not truly black. They glow. Very faintly, but they glow. At the edge of a black hole, right near the boundary we call the event horizon, the fabric of space itself is being stretched and twisted by gravity. And in that extreme environment, something remarkable happens. Particles can appear out of what seems like nothing. Now, particles popping into existence from empty space might sound like science fiction, but it is actually a well-established part of quantum physics. The vacuum of space is not truly empty. It is a bubbling, seething foam of energy where particles and their opposites flicker in and out of existence all the time. Usually, these particles appear in pairs, meet each other, and vanish, again in the blink of an eye. Nobody notices because it all cancels out. But near a black hole, the gravity is so intense that sometimes one of those particles gets pulled across the event horizon, while the other one escapes. The escaping particle carries energy away from the black hole, and that means the black hole loses a tiny bit of mass. Over time, this process slowly drains the black hole, making it lighter and lighter. For a big black hole, this process is incredibly slow. A black hole with the mass of our Sun would take something like 10 to the power of 67 years to evaporate. That is a number so large, it makes the current age of the universe look like the blink of an eye. The universe is only about 14 billion years old. 10 to the 67 years is a 1 followed by 67 zeros. It is an almost unthinkable span of time. But for a very small black hole, the story is different. The smaller a black hole is, the hotter it burns, and the faster it loses mass. A primordial black hole that was born with a very tiny mass in the early universe could have already evaporated completely by now. It would have slowly radiated away all of its energy, getting hotter and hotter as it shrank, until finally, in a last brilliant flash of radiation, it was gone. So when we talk about primordial black holes, we are talking about objects that may or may not still exist. The smaller ones could have vanished long ago. But the bigger ones, the ones that were born with enough mass to survive for billions of years, might still be out there right now, drifting silently through the cosmos. And here is where things get really exciting. Some scientists believe that primordial black holes could be the answer to one of the biggest mysteries in all of science: dark matter. You have probably heard of dark matter before. It is the invisible stuff that makes up about 27% of the total mass and energy of the universe. We cannot see it. We cannot touch it. We cannot detect it with any of our instruments directly. But we know it is there because of the way it pulls on galaxies and bends light. Without dark matter, the galaxies we see would fly apart. They would not have enough gravity to hold themselves together. For decades, scientists have been trying to figure out what dark matter is made of. They have looked for exotic particles. They have built detectors deep underground. They have searched with the most powerful telescopes ever built. And so far, nobody has found a definitive answer. But what if the answer was hiding in plain sight? What if dark matter is not some strange new particle at all? What if it is primordial black holes? The idea is simple and elegant. If the early universe produced enough primordial black holes of a certain size, they could account for all the missing mass we call dark matter. They would be invisible because they do not emit light. They would interact with other matter only through gravity, which is exactly what dark matter does. And they would be spread throughout the universe, just like dark matter is. Now, this idea is still just a hypothesis. Scientists have not proven it yet. There are some mass ranges where primordial black holes have been ruled out as the sole explanation for dark matter. But there are other ranges where they could still be the answer. It is one of those tantalizing possibilities that keeps physicists up at night, wondering if the answer to one of the greatest mysteries has been staring at us from the very beginning. But let us leave the realm of the tiny and the ancient for now. Let us move forward in time, billions of years after the Big Bang, to a universe filled with stars. Because the most common type of black hole in the universe today is not a primordial one. It is the kind that is born from the death of a massive star. These are called stellar mass black holes, and their story begins with fire. Every star you see in the night sky is a furnace. Deep in its core, Atoms of hydrogen are being crushed together with such incredible force that they fuse into helium. This process, called nuclear fusion, releases enormous amounts of energy. It is the reason the sun shines. It is the reason stars glow across the vast emptiness of space. But fusion does more than just make light. It also creates an outward pressure that pushes against the inward pull of gravity. As long as a star is fusing fuel in its core, these two forces are in balance. Gravity pulls inward, trying to crush the star. Radiation pressure pushes outward, trying to blow it apart. And for millions or even billions of years, the star hangs in this delicate equilibrium, shining steadily. But nothing lasts forever. And every star, no matter how bright, will eventually run out of fuel. For a star like our Sun, the end is relatively gentle. When a sun-sized star exhausts its hydrogen, it swells into a red giant, sheds its outer layers, and leaves behind a small, dense remnant called a white dwarf. A white dwarf is about the size of the Earth, but has the mass of a star. It slowly cools over billions of years, fading away like an ember in the dark. But for a much more massive star, a star with more than about 8 times the mass of our Sun, the ending is far more dramatic. When a massive star runs out of hydrogen fuel, it does not simply stop fusing. Instead, it begins fusing heavier and heavier elements. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes neon. Neon becomes oxygen. Oxygen becomes silicon. And silicon becomes iron. Each of these stages happens faster than the last. A massive star might burn hydrogen for millions of years, but it burns through its silicon in just a matter of days. And when the core finally turns to iron, the process stops. Iron is the end of the line. Fusing iron does not release energy. It absorbs it. And the moment the core becomes iron, the star is doomed. Without the outward pressure of fusion to hold it up, the core collapses. In less than a second, the innermost part of the star falls inward at speeds approaching a quarter of the speed of light. The core, which might have been the size of the Earth, is crushed down to a ball just a few miles across. The density becomes unimaginable. A teaspoon of this material would weigh billions of tons. And then the outer layers of the star, which are still falling inward, slam into this suddenly rigid core. The result is a supernova, one of the most powerful explosions in the universe. For a brief time, a single dying star can outshine an entire galaxy of hundreds of billions of stars. The supernova blasts the star's outer layers into space at thousands of miles per second, creating a beautiful, expanding cloud of gas and dust called a supernova remnant. These remnants are the birthplace of future stars and planets. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the cores of massive stars and scattered across the cosmos by supernovae. But what about the core? What happens to that incredibly dense ball of matter left behind after the explosion? If the core has a mass of roughly 1.5 to about 3 times the mass of our Sun, it becomes a neutron star. A neutron star is an object so dense that the atoms themselves have been crushed out of existence. The electrons and protons have been squeezed together to form neutrons, and the entire star is essentially one giant atomic nucleus a few miles across. But if the core is heavier than about 3 solar masses, not even neutron pressure can hold it up. Nothing can. The core continues to collapse, falling past every known barrier, shrinking down to a point of infinite density called a singularity. And around that singularity, the gravity becomes so intense that space itself curves inward, creating a boundary from which nothing, not even light, can escape. That boundary is the event horizon, and the object it defines is a stellar mass black hole. A typical stellar mass black hole has a mass somewhere between about 3 and 50 times the mass of our Sun. Some that form from particularly massive stars or from mergers of neutron stars can be even heavier. But in general, these are the workhorses of the black hole family. They are the most common type we know of, and they are scattered throughout every galaxy in the universe. The Milky Way alone is estimated to contain somewhere around 100 million stellar mass black holes. 100 million, and most of them are completely invisible. They drift through interstellar space, alone and silent, betraying their presence only through the occasional tug of gravity on a nearby star or cloud of gas. But some stellar mass black holes are not alone. Some of them have companion stars, locked in a gravitational embrace. In these systems, called X-ray binaries, the black hole slowly pulls gas off its companion star. The gas spirals inward, forming a swirling disk called an accretion disk. As the gas in the disk gets closer to the black hole, it heats up to millions of degrees and begins to glow brightly in X-ray light. It was through these X-ray binaries that astronomers first found strong evidence for the existence of black holes. In the early 1970s, a powerful X-ray source in the constellation, Cygnus, caught the attention of astronomers. They called it Cygnus X1. After years of careful observation, they determined that it was a stellar mass black hole, roughly 14 times the mass of our Sun, orbiting a giant blue star. Cygnus X1 became the first widely accepted black hole candidate. It was a landmark discovery, the moment black holes went from being a theoretical curiosity predicted by Einstein's equations to a real, observable feature of our universe. Since then, astronomers have found dozens of stellar mass black holes in X-ray binary systems. Each one tells us a little more about how these objects form, how they feed, and how they interact with the matter around them. But X-ray binaries are not the only way we can detect stellar mass black holes. In recent years, a completely new window on the universe has opened up, one that allows us to detect black holes in a way that was once thought impossible. Gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made one of the most important discoveries in the history of science. It detected ripples in the fabric of space-time itself, caused by the collision and merger of two stellar mass black holes more than 1 billion light-years away. Think about that for a moment. Two black holes, each roughly 30 times the mass of the Sun, spiraling toward each other at nearly the speed of light. As they got closer, they orbited faster and faster, whipping around each other hundreds of times per second. The energy released was staggering. In the final fraction of a second before they merged, they radiated more energy in the form of gravitational waves than all the stars in the observable universe were emitting in light at that same moment. And those waves, those tiny ripples in space-time, traveled across the cosmos for over 1 billion years before reaching Earth and making the LIGO detectors vibrate by less than 1,000th the width of a proton. That is the level of precision we are talking about. It is almost beyond comprehension. Since that first detection, LIGO and its partner observatory Virgo have detected dozens more gravitational wave events. Many of them involve the mergers of stellar mass black holes. Some involve the merger of two neutron stars. And some involve a black hole swallowing a neutron star whole. Each detection teaches us something new. We have learned that stellar mass black holes come in a wider range of sizes than we expected. Some of the merging black holes detected by LIGO are surprisingly heavy, with masses of 60 or 70 solar masses, This has forced astronomers to rethink how the most massive stars die and what kinds of black holes they can produce. We have also learned that black hole mergers are not rare events. They happen all over the universe, all the time. The gravitational wave sky is alive with the echoes of these cosmic collisions, a symphony of space-time ripples that we are only now learning to hear. Now, you might be wondering about something. We have talked about primordial black holes and stellar mass black holes. But what about those impossibly massive objects at the centers of galaxies? The ones that weigh millions or billions of times more than our Sun. Those are supermassive black holes, and they are perhaps the most mysterious objects in the entire universe. Every large galaxy in the universe, as far as we can tell, has a supermassive black hole sitting at its center. Our own Milky Way has one. It is called Sagittarius A star, and it has a mass of about 4 million times that of our Sun. That might sound enormous, and it is. But compared to some of the other supermassive black holes out there, Sagittarius A star is actually quite modest. Take the black hole at the center of a galaxy called Messier 87, for example. This beast has a mass of about 6.5 billion times that of our Sun. It is so massive that its event horizon, the point of no return, is larger than our entire solar system. In 2019, the Event Horizon Telescope project captured the first ever image of a black hole's shadow, and it was this monster in Messier 87 that they photographed. That image, a glowing ring of superheated gas surrounding a dark circular void, became one of the most iconic photographs in the history of science. But even Messier 87's black hole is not the biggest we know of. In the center of a galaxy called Holmberg 15A sits a supermassive black hole with an estimated mass of 40 billion suns. 40 billion. That is a number so large that it almost stops meaning anything. To put it in perspective, if you could somehow line up 40 billion of our suns side by side, they would stretch across a distance that would take light years to cross. So how did these monsters form? That is one of the biggest unsolved questions in astronomy. The problem is time. We can see supermassive black holes that existed when the universe was less than 1 billion years old. That means they grew to enormous sizes in a remarkably short period. And growing a black hole from a small stellar mass seed to something billions of times heavier than the Sun is not easy. Even if a black hole were eating constantly, gobbling up gas and stars at the maximum possible rate, it would be very difficult to grow that fast. There is a limit to how quickly a black hole can eat, called the Eddington limit. As matter falls toward a black hole, it heats up and emits radiation. That radiation pushes outward against the infalling matter, creating a kind of cosmic speed limit on how fast the black hole can consume material. To go from a stellar mass black hole to a supermassive one in less than 1 billion years, while respecting the Eddington limit, would require almost continuous feeding at maximum capacity. And that seems unlikely in the chaotic, constantly changing environment of the early universe. So scientists have proposed several alternative ideas for how supermassive black holes formed. One possibility is direct collapse. In the early universe, before the first stars ignited, there were massive clouds of primordial gas, mostly hydrogen and helium. Under the right conditions, some of these clouds might have collapsed directly into black holes without ever forming stars first. These direct collapse black holes could have started with masses of tens of thousands or even hundreds of thousands of solar masses, giving them a huge head start on their growth. Another possibility involves the merging of smaller black holes. If the early universe produced many stellar mass black holes, some of them could have found each other, merged, grown, merged again, and so on. building up to supermassive sizes over time through repeated collisions. And of course, there is the primordial black hole idea we discussed earlier. If some primordial black holes were born with very large masses in the first moments after the Big Bang, they could have served as seeds for the supermassive black holes we see today. The truth is, we do not yet know which of these mechanisms is correct. It might even be a combination of all of them. Different supermassive black holes in different galaxies might have formed in different ways. The universe is a big and varied place, and nature rarely uses just one trick. What we do know is that supermassive black holes play a crucial role in the lives of their galaxies. They are not just passive objects sitting quietly at the center. They are active participants in the evolution of the galaxies around them. When a supermassive black hole is actively feeding, consuming large amounts of gas and dust, it becomes what astronomers call an active galactic nucleus, or AGN. The material swirling around the black hole in its accretion disk gets so hot that it can outshine the entire rest of the galaxy. These brilliant objects are some of the most energetic phenomena in the universe. The most extreme examples of active galactic nuclei are called quasars. A quasar is a supermassive black hole that is feeding so voraciously that the energy output from its accretion disk is almost beyond belief. A single quasar can be hundreds of times brighter than the entire Milky Way galaxy, which contains somewhere around 200 billion stars. Quasars were more common in the early universe, when there was more gas available for black holes to consume. Most of the quasars we see are billions of light years away, which means we are seeing them as they were billions of years ago. They are like cosmic fossils, snapshots of a younger, more violent universe. But the influence of supermassive black holes goes beyond just producing light. Some of them also produce jets, enormous beams of material and energy that shoot out from the black hole's poles at nearly the speed of light. These jets can extend for millions of light years, far beyond the boundaries of their host galaxy. They carry tremendous amounts of energy and can heat up the gas in the space between galaxies, preventing it from cooling down and forming new stars. This feedback process, where the energy from the black hole influences the gas around it, is thought to be one of the key mechanisms that regulates the growth of galaxies. Without it, galaxies might grow too large, forming too many stars too quickly. The black hole, in a sense, acts like a thermostat, controlling the temperature and behavior of the gas in and around its galaxy. It is a remarkable relationship. The galaxy feeds the black hole by channeling gas toward its center, and the black hole regulates the galaxy by pumping energy back out into its surroundings. This dance between black hole and galaxy has been going on for billions of years, shaping the structure of the universe we see today. There is also an intriguing correlation that hints at just how closely connected supermassive black holes and their galaxies are. The mass of a supermassive black hole is almost always a small but consistent fraction of the total mass of the central bulge of stars in its galaxy. This relationship holds across a wide range of galaxy sizes, from small ones to enormous ones. It is as if the black hole and the galaxy somehow know about each other, growing in lockstep through cosmic history. How this correlation arises is still being studied, but it suggests that the formation and evolution of galaxies and their central black holes are deeply intertwined. You cannot understand one without understanding the other. Now, so far, we have talked about two size classes of black holes. The stellar mass ones, which range from a few to maybe 100 solar masses, and the supermassive ones, which start at hundreds of thousands of solar masses and go up to tens of billions. But what about the gap in between? What about black holes with masses of hundreds or thousands of solar masses? These are called intermediate mass black holes. And for the longest time, they were the missing link of the black hole world. The problem was simple. We had plenty of evidence for stellar mass black holes. We had overwhelming evidence for supermassive black holes. But we could not find anything convincingly in between. And that was strange, because you would expect nature to produce black holes in a continuous range of sizes, just like it produces stars in a continuous range of sizes. So where were the intermediate mass black holes hiding? Part of the difficulty is that intermediate mass black holes are harder to detect than their bigger and smaller cousins. Stellar mass black holes often reveal themselves through X-ray binaries, where they are actively pulling matter off a companion star. Supermassive black holes reveal themselves through the spectacular activity at the centers of galaxies. But an intermediate mass black hole, sitting somewhere in a star cluster or drifting through a galaxy, might not have a convenient companion or a ready supply of gas to give away its position. But astronomers kept looking, and slowly, evidence began to accumulate. One of the most promising places to search for intermediate mass black holes is in globular clusters. These are dense, ancient collections of hundreds of thousands to millions of stars, bound together by gravity. They orbit around the outskirts of galaxies and are among the oldest structures in the universe. In the crowded environments of globular clusters, stars interact with each other frequently. Massive stars tend to sink toward the center of the cluster, a process called mass segregation. And if enough massive stars accumulate in the center, they can merge with each other, forming objects of extraordinary mass that might eventually collapse into intermediate mass black holes. In 2020, LIGO and Virgo detected a gravitational wave signal called GW19CHO521. It was the merger of two black holes with masses of about 85 and 66 solar masses. The resulting black hole had a mass of about 142 solar masses, making it the first ever intermediate mass black hole detected through gravitational waves. This was a breakthrough discovery. Not only did it prove that intermediate mass black holes exist, it also raised fascinating questions about how such heavy stellar mass black holes could form in the first place. A star that is heavy enough to produce an 85 solar mass black hole would normally be expected to blow itself apart in a different kind of explosion, called a pair instability supernova, which would leave no remnant at all. The fact that LIGO detected such a heavy black hole suggests that it might not have formed from a single star, but rather from a previous merger of smaller black holes. This idea of hierarchical merging, where black holes merge to form bigger black holes, which then merge again to form even bigger ones, could be the mechanism by which intermediate mass black holes grow. In the dense environments of star clusters, where black holes can find each other relatively easily, this process could build up black holes of hundreds or even thousands of solar masses over time. There is also evidence from X-ray observations. In some galaxies, astronomers have found extremely bright X-ray sources that are too luminous to be powered by a stellar mass black hole, but not bright enough to be a full-blown active galactic nucleus. These objects, called ultraluminous X-ray sources, or ULXs, might be powered by intermediate mass black holes actively feeding on nearby gas. One of the most compelling candidates is an object called HLX-1, located in a galaxy about 300 million light-years away. Its X-ray brightness and behavior are consistent with a black hole of perhaps 10,000 to 100,000 solar masses, placing it firmly in the intermediate mass range. So the evidence is building. Intermediate mass black holes exist, They may be less common or harder to find than the other types. If you find yourself coming back to videos like this one to fall asleep, there's a reason. Your mind needs somewhere to go. Not music, not silence. Something steady to follow. Beyond the Stars is a full collection of overnight narrated space journeys. 5 tracks, 6 to 8 hours each. No ads, no endings, no interruptions. $39, once, any device. Link is in the description. We'll be back in a moment, but they are out there, filling in the gap between the stellar and the supermassive, completing the family portrait of black holes across the cosmic mass spectrum. But the story of black holes does not end with their sizes. There is another way to classify them that has nothing to do with how much they weigh. It has to do with how they behave. Specifically, whether they spin, and nearly all of them do. This should not be surprising. Almost everything in the universe spins. The Earth spins, the Sun spins. Galaxies spin. It is a natural consequence of the way things form. When a cloud of gas collapses to form a star, any tiny bit of rotation it had gets amplified as it shrinks, just like an ice skater who pulls in their arms and spins faster. The same thing happens when a star collapses to form a black hole. Whatever rotation the star had gets compressed into a much smaller space, and the resulting black hole can spin incredibly fast. Some black holes are believed to rotate at nearly the speed of light, spinning hundreds or even thousands of times per second. The physics of spinning black holes is different from that of non-spinning ones. A non-spinning black hole described by what is called the Schwarzschild solution to Einstein's equations is perfectly spherical. Its event horizon is a simple sphere, and everything about it is determined solely by its mass. But a spinning black hole described by the Kerr solution is more complex. Its event horizon is slightly flattened at the poles, like a ball that has been gently squeezed, and around it there is a region called the ergosphere, a zone of drag space-time where nothing can stand still. Even light itself, if it enters the ergosphere, is forced to move in the direction of the black hole's rotation. Space itself is being dragged along. The ergosphere is a strange and wonderful place. An object that enters the ergosphere can actually extract energy from the black hole's rotation through a process called the Penrose process. In theory, an advanced civilization could toss material into the ergosphere in just the right way, have part of it fall into the black hole while the rest is flung outward with more energy than it went in with. The extra energy comes from the black hole's rotation, which slows down slightly as a result. This idea, first proposed by physicist Roger Penrose in 1969, has captured the imagination of science fiction writers and physicists alike. It suggests that spinning black holes are not just cosmic garbage disposals. They are potential energy sources of incredible power, if only we had the technology to tap into them. In practice, the Penrose process is extremely difficult to exploit. You would need to get close to a spinning black hole, survive the extreme tidal forces, and execute a precisely timed maneuver in one of the most hostile environments in the universe. But the fact that the physics allows it is remarkable. There are also theoretical classes of black holes defined by their electric charge. A non-spinning charged black hole is described by the Reissner-Nordstrom solution. A spinning charged black hole is described by the Kerr-Newman solution. Together with the Schwarzschild and Kerr solutions, these 4 types represent all the possible mathematical descriptions of a black hole in general relativity. In reality, though, black holes with significant electric charge are probably extremely rare or non-existent. Any charged black hole would quickly attract particles of the opposite charge, neutralizing itself. So when we talk about real black holes in the universe, We are almost always talking about Kerr black holes, the spinning, uncharged variety. But there is a beautiful simplicity here that is worth pausing to appreciate. All black holes, regardless of how they formed, regardless of what fell into them, regardless of their history, can be described by just three numbers: mass, spin, charge. That is it. Everything else, every detail about the star that formed the black hole, every atom that fell into it, every photon it ever absorbed, all of that information is erased. This principle is known as the no-hair theorem, and it is one of the most striking results in all of physics. A black hole made from a collapsing star and a black hole made from a collapsing gas cloud in the early universe, if they have the same mass, spin, and charge, are completely indistinguishable. The black hole has no memory of its past. It is, in a sense, the ultimate clean slate. This raises profound questions about the nature of information in the universe. If information is supposed to be conserved, if the laws of physics say that information can never truly be destroyed, then what happens to all the information that falls into a black hole? Is it gone forever? Or is it somehow encoded in the Hawking radiation that the black hole slowly emits as it evaporates? This question is known as the black hole information paradox, and it has been one of the central puzzles in theoretical physics for nearly 50 years. Hawking himself initially argued that the information was simply lost, which horrified many physicists because it violated a fundamental principle of quantum mechanics. Later, Hawking changed his mind and accepted that the information probably does survive, though exactly how it is preserved and recovered remains unclear. Some physicists believe the answer lies in a concept called the holographic principle, which suggests that all the information about the interior of a black hole is somehow encoded on its surface, on the event horizon itself. In this view, the event horizon is not just a boundary. It is a two-dimensional screen that contains a complete record of everything the black hole has ever swallowed. The three-dimensional interior is, in some sense, a projection of this two-dimensional surface. This is a deeply strange and counterintuitive idea, but it has gained significant support from theoretical work in string theory and quantum gravity. If it is correct, it would mean that black holes do not actually destroy information. They just store it in a way that is incredibly difficult to read. But we are getting deep into the realm of theory now, and our journey is far from over. There are still more kinds of black holes to explore, and some of them are not sitting quietly at the center of a galaxy or orbiting a companion star. Some of them are on the move. Let us talk about rogue black holes. A rogue black hole is exactly what it sounds like. It is a black hole that has been kicked out of its home and is wandering freely through space, unbound to any star, any binary system, or any galactic center. It is a cosmic drifter moving through the darkness with nothing to give away its presence except its gravity. How does a black hole become a rogue? There are several ways. For stellar mass black holes, the most common mechanism is the supernova kick. When a massive star explodes, the explosion is not perfectly symmetrical. There is often a slight asymmetry, with more material being ejected in one direction than another. This gives the newly formed black hole or neutron star a push, like a rocket engine firing in one direction. If the kick is strong enough, the black hole can be ejected from its binary system or even from the star cluster where it was born, sending it sailing off into interstellar space at high speed. For supermassive black holes, the mechanism is different and even more dramatic. When two galaxies merge, their central supermassive black holes eventually sink toward the center of the merged galaxy and begin to orbit each other. As they spiral closer, they emit gravitational waves, and the emission of those waves carries momentum. If the emission is not perfectly symmetrical, which it usually is not, the merged black hole gets a gravitational recoil kick. In extreme cases, this kick can be strong enough to eject the newly formed black hole from the galaxy entirely, sending it hurtling through intergalactic space at thousands of miles per second. Imagine that for a moment, a black hole weighing millions or billions of times more than the Sun, flung out of its galaxy like a stone from a slingshot, traveling through the empty void between galaxies. No stars, no gas, no light, just an invisible giant, plowing through the cosmic wilderness at incredible speed. We have actually found evidence for this. In 2023, astronomers using the Hubble Space Telescope spotted something extraordinary, a linear streak of new stars stretching 200,000 light-years across intergalactic space. The trail was twice the diameter of our entire Milky Way galaxy. At one end of the trail was what appeared to be a runaway supermassive black hole, plowing through tenuous intergalactic gas and compressing it enough to trigger star formation in its wake. It was like finding the contrail of an invisible jet aircraft, except the aircraft was a supermassive black hole, and the contrail was a chain of newborn stars stretching across the cosmos. And then, in 2022, astronomers confirmed the first detection of an isolated stellar mass black hole wandering through our own Milky Way galaxy. Using a technique called gravitational microlensing, where the gravity of a foreground object briefly magnifies the light of a background star, a team led by researchers at the Space Telescope Science Institute identified a dark, massive object about 5,000 light-years from Earth. Careful measurements over more than a decade confirmed that this object was about 7 times the mass of the Sun and emitted no light of its own. It was a lone black hole, drifting silently through the galaxy. This was not entirely unexpected. Theoretical models have long predicted that there should be hundreds of millions of stellar mass black holes wandering through the Milky Way, remnants of ancient supernovae, whose natal kicks sent them sailing off into the void. But detecting them is extraordinarily difficult because they are completely dark. The gravitational microlensing technique offers one of the few ways to find them. As a rogue black hole passes in front of a more distant star, its gravity bends and magnifies the star's light in a distinctive way. By carefully monitoring millions of stars over long periods, astronomers can spot these telltale brightening events and work backward to determine the mass and nature of the invisible lens. Future missions, including the Nancy Grace Roman Space Telescope, are expected to find many more of these dark wanderers, giving us a much better picture of just how many rogue black holes are out there in our galaxy. But rogue black holes are not the only unusual members of the black hole family. There are also black holes that come in pairs and in triples. Binary black holes are systems where 2 black holes orbit each other, bound by their mutual gravity. They can form in several ways. 2 massive stars in a binary system might each collapse to form black holes, leaving behind a binary black hole. Or 2 separate black holes in a dense star cluster might be brought together by gravitational interactions with surrounding stars. Binary black holes are the sources of the gravitational waves detected by LIGO and Virgo. As the 2 black holes spiral closer together, they emit increasingly strong gravitational waves, losing energy and tightening their orbit. Eventually, they merge in a violent collision, forming a single, larger black hole and releasing a tremendous burst of gravitational wave energy. The eyes and final seconds of a binary black hole merger are among the most energetic events in the universe. The two black holes are orbiting each other at a significant fraction of the speed of light, and the gravitational wave emission reaches a crescendo in what physicists call the chirp, a rapidly rising frequency that matches the increasing orbital speed. After the merger, the newly formed black hole is not immediately settled. It is vibrating like a bell that has just been struck. These vibrations, called ringdown, produce additional gravitational waves as the black hole radiates away its excess energy and settles into a stable shape. The frequency and damping time of the ringdown waves depend only on the mass and spin of the final black hole, providing a direct test of general relativity's predictions. Triple black hole systems are rarer but not unheard of. When three galaxies merge, their central black holes can end up in a complex three-body gravitational dance. In some cases, two of the black holes form a tight binary, while the third orbits farther out. In other cases, the gravitational interactions can eject one of the black holes entirely, turning it into a rogue. These multi-black hole systems are important because they may help explain how supermassive black holes grow so quickly. The interactions between multiple black holes can speed up the merger process, allowing black holes to combine and grow faster than they would in simple binary systems. Now, let us shift our attention to something that might seem like a contradiction. Black holes are defined by the fact that nothing can escape them. And yet, some of the brightest objects in the universe are powered by black holes. We have already talked about quasars and active galactic nuclei, but there are even more extreme examples. Consider blazars. A blazar is a special kind of active galactic nucleus, where one of the black hole's jets is pointed almost directly at us, straight down the barrel. Because the material in the jet is moving at nearly the speed of light, the light it emits gets boosted enormously by relativistic effects. The result is a blinding point of light that can vary in brightness on timescales of hours or even minutes. Blazars are some of the most distant and luminous objects we can see. They are also important sources of high-energy particles, including cosmic rays and neutrinos that rain down on Earth from across the universe. Then there are tidal disruption events. These happen when a star wanders too close to a supermassive black hole. The black hole's tidal forces, the difference in gravitational pull between the near side and the far side of the star, are so extreme that they literally tear the star apart. The star gets stretched into a long, thin stream of gas, a process sometimes called spaghettification. Some of this gas falls into the black hole, forming a temporary accretion disk that flares brilliantly before fading away over weeks or months. Tidal disruption events are like cosmic fireworks. They give us a brief, intense view of a supermassive black hole that might otherwise be dormant and invisible. They also provide valuable information about the mass of the black hole and the properties of the destroyed star. Astronomers have now detected dozens of these events, and they are discovering them at an increasing rate thanks to new survey telescopes that scan the sky every night, looking for sudden changes in brightness. Each event is unique, and some have produced surprising results, including evidence for rogue black holes that are not at the center of their galaxies. Now, let us talk about something truly mind-bending. What happens inside a black hole? This is a question that pushes us to the very limits of what we know. Our best theory of gravity, Einstein's general relativity, tells us that at the center of every black hole is a singularity, a point of infinite density where the laws of physics as we know them break down. The curvature of space-time becomes infinite. Tidal forces become infinite. Everything that falls into the black hole is crushed into this single dimensionless point. But many physicists believe that the singularity is not a real physical object. It is a sign that our theory is incomplete. General relativity works beautifully in most situations, but in the extreme conditions inside a black hole, it reaches its limits. We need a theory of quantum gravity, a theory that combines general relativity with quantum mechanics to truly understand what happens at the center of a black hole. We do not yet have a complete theory of quantum gravity. It is one of the great unsolved problems in physics, the holy grail that has eluded some of the greatest minds in science for decades. But there are promising approaches. String theory, loop quantum gravity, and other frameworks all offer tantalizing hints about what the interior of a black hole might really look like. Some of these theories suggest that the singularity might be replaced by something else. Perhaps matter inside a black hole reaches an incredibly high but finite density, forming a kind of quantum bounce rather than a true singularity. Perhaps the interior connects to another region of space-time, like a wormhole. Or perhaps the concept of space and time itself breaks down in a way that we cannot even visualize. For now, the interior of a black hole remains the ultimate terra incognita, the last unexplored frontier of the physical universe. We can peer right up to the edge of the event horizon, but we cannot look beyond it. Whatever secrets lie inside are hidden from us, perhaps forever. But even if we cannot look inside, we can learn a remarkable amount about black holes by studying their edges. The event horizon is one of the most important and fascinating boundaries in all of physics. It is not a physical surface. It is not a wall or a membrane. It is simply the mathematical boundary beyond which the escape velocity exceeds the speed of light. For a stellar mass black hole of about 10 solar masses, the event horizon has a radius of about 30 kilometers. That means all the matter of 10 suns is compressed into a sphere smaller than a mid-sized city. The density at the event horizon is already mind-boggling, and it only gets more extreme as you move inward. For a supermassive black hole, the event horizon can be much larger. The supermassive black hole at the center of Messier 87 has an event horizon radius of about 20 billion kilometers, which is larger than the orbit of Pluto around our Sun. Counterintuitively, the density at the event horizon of a supermassive black hole is actually quite low. You could cross the event horizon of a sufficiently large black hole without even noticing, at least at first. There would be no flash of light, no sudden sensation of compression. The tidal forces at the event horizon of a supermassive black hole are gentle enough that a human body could survive the crossing intact. But do not be fooled by that gentleness. Once you cross the event horizon, there is no going back. Every possible path through space-time, every direction you could travel, no matter how powerful your engines, leads inward toward the singularity. Even light, moving at the fastest speed possible, cannot escape. Time and space inside the event horizon are rearranged in such a way that falling toward the singularity is not a direction in space. It is a direction in time. Hitting the singularity is not about where you are going. It is about when you are going, and you are going there inevitably. This is perhaps the most unsettling thing about black holes. It is not just that they trap things. It is that once you are inside, the future itself has been rearranged so that the singularity is the only possible destination. There is no escape, not because the walls are too high, but because the road only goes one way. Let us move to another fascinating topic: black holes and time. One of the most remarkable predictions of general relativity is that gravity affects the passage of time. The stronger the gravitational field, the slower time passes. This is not science fiction. It is a proven scientific fact, confirmed by numerous experiments. GPS satellites, for example, have to account for the difference in the passage of time between their orbits and the surface of the Earth. Without this correction, GPS would be inaccurate by several miles per day. Near a black hole, this effect is taken to an extreme. As you approach the event horizon, time slows down dramatically relative to a distant observer. If someone far away were watching you fall toward a black hole, they would see you moving slower and slower, your image becoming dimmer and redder as the light you emit gets stretched by the intense gravity. You would appear to freeze at the event horizon, never quite crossing it, your image lingering there as an ever fainter ghost. From your own perspective, though, everything would be perfectly normal. You would cross the event horizon in a finite amount of time and continue falling inward. The disconnect between what you experience and what a distant observer sees is one of the most striking consequences of general relativity, and one of the things that makes black holes so deeply strange. This time dilation effect also plays a role in the appearance of accretion disks. Material orbiting close to the event horizon moves at nearly the speed of light and experiences extreme time dilation. The light it emits gets shifted to different frequencies, creating the characteristic bright ring and dark shadow that we see in images of black holes. Now, let us return to the cosmic zoo and look at some of the more exotic black hole phenomena that make astronomers scratch their heads. We have already mentioned that when galaxies merge, their supermassive black holes can end up in a binary system, slowly spiraling toward each other. But this process is not always smooth. In fact, there is a well-known problem in astrophysics called the final parsec problem. Here is the issue. When two supermassive black holes are far apart, they lose energy through interactions with surrounding stars, which helps them spiral closer together. And when they are very close, they lose energy through gravitational wave emission, which brings them together quickly. But in between, at a distance of about 1 parsec, or roughly 3 light years, there is a gap where neither mechanism is very efficient. The black holes can get stuck at this distance, orbiting each other for a very long time without merging. This is the final parsec problem, and it has puzzled astronomers for years. If the process really does stall at this distance, then many binary supermassive black holes in the universe should be stuck in this limbo, unable to complete their merger. However, recent work suggests that the problem may not be as severe as once thought. If the galaxy that hosts the binary is not perfectly spherical, but instead has some aspherical structure, like a disk or a bar, then stars can interact with the binary from a wider range of angles, providing more opportunities to extract energy and push the black holes closer together. Computer simulations have shown that in realistic, non-spherical galaxies, the binary can usually overcome the final parsec barrier and merge within a few 100 million years, and we may have direct evidence that this process works. In 2023, several teams of astronomers using pulsar timing arrays, networks of extremely precise radio telescopes that monitor the rhythmic flashing of distant pulsars, announced the detection of a low-frequency gravitational wave background. This background is a cosmic hum, a blend of gravitational waves from many binary supermassive black holes throughout the universe, all slowly spiraling toward each other. The detection of this gravitational wave background is one of the most exciting recent discoveries in astrophysics. It tells us that binary supermassive black holes are indeed merging throughout the cosmos, producing a chorus of gravitational waves that fills the universe like a constant, low rumbling vibration. Let us now move to one of the most fascinating and terrifying kinds of black holes, the kind that eats. We have talked about accretion disks and jets, But let us take a closer look at what happens when a black hole actively feeds. The process is incredibly violent and incredibly energetic. When gas falls toward a black hole, it does not fall straight in. Because of angular momentum, the gas spirals inward, forming a flat, rotating disk around the black hole. This is the accretion disk. Friction within the disk heats the gas to extraordinary temperatures. The inner regions of the disk around a stellar mass black hole can reach temperatures of millions of degrees, hot enough to emit X-rays. Around a supermassive black hole, the temperatures are somewhat lower, but the total energy output is staggering. The accretion disk of a luminous quasar can convert about 10% of the rest mass energy of the infalling matter into radiation. To put that in perspective, nuclear fusion in stars converts less than 1% of the rest mass energy of hydrogen into light. Accretion onto a black hole is 10 times more efficient than nuclear fusion. It is the most efficient energy generation process known to physics, short of matter-antimatter annihilation. This is why quasars are so bright. They are not just burning fuel. They are converting mass directly into energy, with an efficiency that dwarfs anything else in nature. But not all of the infalling gas makes it into the black hole. Some of it gets channeled along the black hole's magnetic field lines and launched outward in the form of relativistic jets. These jets carry a combination of charged particles and electromagnetic radiation, and they can extend for millions of light years into intergalactic space. The exact mechanism that produces these jets is still not fully understood, but it is believed to involve the interaction between the accretion disk and the spinning black hole's magnetic field. The Blandford-Nyack process, proposed in 1977, describes how the rotational energy of a spinning black hole can be extracted through magnetic field lines that thread the event horizon, powering the jets. These jets are not just impressive to look at. They have a real impact on the universe. When a jet slams into the intergalactic medium, the gas between galaxies, it creates enormous shock waves that heat the gas and prevent it from cooling. This suppresses star formation in the surrounding area, sometimes across an entire galaxy cluster. The energy deposited by a single set of jets can be equivalent to billions of supernovae. This process, called AGN feedback, is now recognized as one of the most important mechanisms in galaxy evolution. It helps explain why the most massive galaxies in the universe are not forming new stars very actively, even though they sit in regions with abundant hot gas. The jets from their central black holes are keeping that gas too hot to condense and form stars. It is a stunning example of how objects that are tiny compared to a galaxy, a black hole might be a millionth the mass of its host galaxy, can have an outsized influence on the cosmos. Now, let us talk about the anatomy of a black hole in a bit more detail. We have mentioned the singularity and the event horizon, but there are other important features worth exploring. The photon sphere is a region just outside the event horizon, where light can orbit the black hole. At this distance, the gravity is strong enough to bend the path of a photon into a circular orbit, but not quite strong enough to pull it in. A photon that enters the photon sphere on just the right trajectory will orbit the black hole indefinitely, circling around and around in a ring of trapped light. In practice, the photon sphere is unstable. Any tiny disturbance will cause the orbiting photon to either spiral into the black hole or fly off into space. But the photon sphere is important because it defines the boundary of the black hole's shadow, the dark silhouette that the Event Horizon Telescope was able to photograph. The shadow of a black hole is not the event horizon itself. It is actually about 2.5 times the size of the event horizon. This is because photons that pass near the photon sphere get bent inward, creating a larger dark region than the event horizon alone would produce. The glowing ring around the shadow in the event horizon telescope images is light from the superheated gas in the accretion disk. Some of this light comes from gas on the far side of the black hole, which has been bent around by the extreme gravity, so that it appears to glow above and below the shadow. It is a stunning visual representation of the warping of space-time. Another important feature is the innermost stable circular orbit, or ISCO. This is the closest orbit that matter can maintain around a black hole without spiraling inward. For a non-spinning black hole, the ISCO is at 3 times the radius of the event horizon. For a maximally spinning black hole where the matter is orbiting in the same direction as the spin, the ISCO moves inward, closer to the event horizon. This means that spinning black holes can extract energy from matter at closer distances, making them even more efficient energy generators. The position of the ISCO has a direct effect on how bright an accretion disk can be. Because gas inside the ISCO falls rapidly into the black hole without radiating much additional energy, the brightness of the accretion disk is determined largely by how much energy is released as the gas spirals from the outer disk down to the ISCO. A black hole with a smaller ISCO, one that is spinning rapidly, can extract more energy and produce a brighter disk. This is one of the ways astronomers can measure the spin of real black holes. By studying the X-ray emission from the inner regions of accretion disks and fitting models to the observed spectra, they can estimate how close the ISCO is to the event horizon, and therefore how fast the black hole is spinning. Several black holes have been measured to be spinning at more than 90% of the maximum possible rate, which is an incredible feat of cosmic engineering by gravity and angular momentum. Let us now delve into one of the most enchanting and strange ideas related to black holes: wormholes. The mathematics of general relativity allows for solutions where a black hole connects to another region of space-time through a tunnel called a wormhole, or more formally, an Einstein-Rosen bridge. In the simplest picture, you would enter the event horizon of a black hole and, instead of hitting a singularity, you would pass through a throat and emerge from a white hole in a different part of the universe, or even in a different universe entirely. It is a breathtaking idea, and it has fueled countless science fiction stories. But we need to be careful here. Just because the math allows for something does not mean it actually happens in nature. The problem with Einstein-Rosen bridges is that they are unstable. In the simplest solutions, the wormhole exists for only a brief instant before pinching shut. Anything trying to travel through it would be crushed by the collapsing throat before it could make it to the other side. Some physicists have proposed that a special type of matter called exotic matter, matter with negative energy density, could stabilize a wormhole and keep it open. But we have never observed exotic matter in nature, and it may not be physically possible for it to exist in the quantities needed to prop open a wormhole. So for now, wormholes remain firmly in the realm of theoretical speculation. They are mathematically fascinating but physically unlikely. No astronomical observations have ever provided evidence for their existence. Still, the idea that black holes might be more than just dead ends, that they might connect different parts of the cosmos, is too beautiful to entirely dismiss. And as our understanding of quantum gravity improves, who knows what surprises might be lurking in the math? Now, let us talk about one of the most visually stunning phenomena associated with black holes: gravitational lensing. General relativity tells us that mass curves space-time, and that light follows the curves of space-time. So when light from a distant star or galaxy passes near a massive object like a black hole, its path gets bent. The massive object acts like a cosmic lens, focusing and distorting the light that passes around it. This effect has been observed many times with galaxies and galaxy clusters acting as lenses. But black holes are particularly powerful gravitational lenses because their gravity is so concentrated. If a black hole passes directly between us and a distant star, the star's light gets bent around the black hole on all sides, creating a ring of light called an Einstein ring. If the alignment is not perfect, the result is a series of distorted and magnified images of the background object. Gravitational microlensing, a smaller scale version of this effect, is one of the few ways we can detect rogue black holes that are not actively feeding. As a lone black hole drifts through the galaxy and passes in front of a distant star, the star's brightness temporarily increases and its apparent position shifts slightly. By monitoring these changes over time, astronomers can determine the mass of the invisible object and confirm whether it is a black hole. This technique is painstaking. It requires monitoring millions of stars simultaneously and waiting for the rare event when a black hole happens to pass in front of one of them. But with modern survey telescopes and space observatories, it is becoming increasingly practical. In the coming decades, we expect to catalogue many more rogue black holes in the Milky Way using gravitational microlensing, building up a census of these invisible inhabitants of our galaxy. Let us now turn our attention to a question that sounds simple, but is actually quite deep. How many black holes are there in the universe? The honest answer is that we do not know exactly, but we can make some educated estimates. In the Milky Way alone, based on the number of massive stars that have lived and died over the galaxy's history, astronomers estimate that there should be somewhere between 100 million and 1 billion stellar mass black holes. Most of them are dark and alone, drifting through the galaxy without any companion to reveal their presence. Our galaxy also has its central supermassive black hole, Sagittarius A star, with a mass of about 4 million solar masses. And there may be a handful of intermediate mass black holes lurking in globular clusters or the remnants of consumed dwarf galaxies. Now multiply that by the number of galaxies in the observable universe. There are estimated to be about 2 trillion galaxies in the observable universe. If each one has a similar population of black holes, the total number of stellar mass black holes in the cosmos could be somewhere around 100 trillion or more. And each large galaxy has its own supermassive black hole, adding another 2 trillion or so to the count. These numbers are staggering. The universe is full of black holes. They are everywhere, woven into the fabric of every galaxy, orbiting in binary systems, hiding in star clusters, wandering alone through the void. We are surrounded by them, even if we cannot see them. And that brings up an important point about how we study these objects. For most of the history of astronomy, we could only observe the universe through light. Visible light, radio waves, X-rays, infrared, all forms of electromagnetic radiation. And since black holes do not emit light on their own, they were always indirect targets. We could see the effects of black holes on their surroundings, the glow of accretion disks, the whipping of companion stars, the brightening of background stars through microlensing, but we could never observe the black holes themselves. That changed with the detection of gravitational waves. For the first time, we could observe black holes directly, not through their effects on light, but through the ripples they create in space-time itself. Gravitational wave astronomy is still very young, but it has already transformed our understanding of black holes in just a few short years, and it is only going to get better. the next generation of gravitational wave detectors, including the space-based Laser Interferometer Space Antenna, or LISA, will be sensitive to much lower frequency gravitational waves than LIGO can detect. LISA will be able to hear the mergers of supermassive black holes, events that release more energy than any other phenomenon in the universe. It will also be able to detect the slow spiraling of binary supermassive black holes, mapping out the population of these cosmic giants across the universe. Between LIGO, LISA, the Event Horizon Telescope, and next-generation observatories, we are entering a golden age of black hole research. We are learning more about these objects now than at any point in history, and the pace of discovery is only accelerating. But let us take a step back from the details and think about the big picture. What role do black holes play in the story of the universe? At first glance, black holes might seem like cosmic destroyers, objects that consume everything and give nothing back. But that is not really accurate. Black holes are actually constructive forces in the universe. They build as much as they destroy. Supermassive black holes, through their jets and radiation, regulate the flow of gas in galaxies, controlling when and where new stars form. Without this regulation, galaxies would be very different places. Some would form too many stars too quickly and burn out. Others would grow too large and diffuse. The black holes at their centers act as governors, keeping things in balance. Stellar mass black holes, through the supernovae that create them, spread heavy elements across the cosmos. The iron, carbon, oxygen, and other elements forged in the cores of massive stars are blasted into space when those stars die, seeding the interstellar medium with the raw materials for new stars, new planets, and eventually new life. Even the gravitational waves produced by merging black holes carry information about the fundamental nature of gravity, testing Einstein's theories in the most extreme conditions possible. Every detection is an experiment, a probe of the fabric of space-time itself. Black holes are not destroyers. They are engines of cosmic evolution, driving the processes that shape the universe from the largest scales to the smallest. Let us now explore some of the recent discoveries that have expanded our understanding of black holes. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole shadow. The target was the supermassive black hole in Messier 87, and the image showed a bright ring of emission surrounding a dark central shadow, just as general relativity predicted. It was a spectacular confirmation of a theory that had been proposed over a century earlier. In 2022, the same collaboration released an image of Sagittarius, a star, the supermassive black hole at the center of our own Milky Way. This was an even more challenging target because Sagittarius A star is much smaller and more variable than the one in Messier 87. The gas swirling around it changes on timescales of minutes, making it difficult to construct a stable image. But the team succeeded, giving us our first look at the shadow of our own galaxy's central black hole. These images are not photographs in the traditional sense. They are reconstructed from radio wave observations made by a network of telescopes spread across the globe, effectively creating a virtual telescope the size of the Earth. The resolution required to see these black hole shadows is equivalent to being able to read a newspaper in New York from a cafe in Paris. Another recent breakthrough came from LIGO's detection of events that challenged our understanding of stellar evolution. Some of the merging black holes detected had masses in a range that was thought to be forbidden. Stars in a certain mass range were expected to be completely destroyed by pair instability supernovae, leaving no remnant at all. The fact that LIGO found black holes in this mass gap suggests that our models of stellar death are incomplete, or that these black holes were formed through some other process, like previous mergers. And then there are the recent discoveries of supermassive black holes in the very early universe, seen by the James Webb Space Telescope. JWST has found active galactic nuclei powered by supermassive black holes that existed when the universe was less than 500 million years old. These black holes are much more massive than expected for such an early epoch, and their existence is difficult to explain with standard models of black hole growth. They suggest that the seeds of supermassive black holes must have been very large, perhaps formed through direct collapse or primordial processes, and that they grew rapidly in the dense, gas-rich environment of the early universe. These discoveries are reshaping our understanding of how the first black holes formed and how they grew to become the monsters we see today. They are a reminder that the universe is full of surprises, and that our current models, while impressively successful, are still works in progress. Now, let us look ahead. Far, far ahead. What is the ultimate fate of black holes? We talked earlier about Hawking radiation, the slow process by which black holes radiate away their mass. For the black holes we see today, this process is incomprehensibly slow. The universe is currently about 13.8 billion years old, and no stellar mass or supermassive black hole has had anywhere near enough time to evaporate. But the universe has a lot of time ahead of it. A lot of time. In the far future, long after the last stars have burned out, long after the last white dwarfs have cooled to absolute zero, long after the last planets have been flung into the void by gravitational perturbations, the universe will enter what cosmologists call the black hole era. In this unimaginably distant future, the only objects still emitting energy will be black holes. Stellar mass black holes, the remnants of long dead stars, will glow faintly with Hawking radiation. Supermassive black holes, the hearts of long dead galaxies, will be the last significant concentrations of matter in the cosmos. The temperature of the Hawking radiation from a solar mass black hole is only about 60 billionths of a degree above absolute zero. That is far cooler than the current temperature of the cosmic microwave background radiation, which is about 2.7 degrees above absolute zero. Right now, black holes are actually gaining energy from the cosmic background faster than they lose it through Hawking radiation. They are getting slightly heavier, not lighter. But the universe is expanding, and as it does, the cosmic background radiation is getting cooler. Eventually, trillions of years from now, the background radiation will drop below the Hawking temperature of even the most massive black holes. At that point, the black holes will begin to lose mass faster than they gain it, and the long, slow process of evaporation will begin in earnest. A stellar mass black hole will take about 10 to the power of 67 years to evaporate. That is a number with 67 zeros. A supermassive black hole of 1 billion solar masses will take about 10 to the power of 100 years. Written out, that is a 1 followed by 100 zeros. It is called a googol, and even that word fails to capture the absurdity of such a span of time. And yet, the universe will endure. It will expand and cool and darken, and the black holes will slowly, imperceptibly, fade away, particle by particle, photon by photon, until finally, the last black hole emits its final burst of Hawking radiation and vanishes. What happens at the very end of a black hole's evaporation is one of the great unsolved questions in physics. As the black hole gets smaller, it gets hotter, radiating more and more energetically. In its final moments, the black hole reaches a temperature so extreme that it begins to emit every kind of particle imaginable. The final burst of energy is expected to be a flash of high-energy radiation, a brief, brilliant farewell from an object that spent an eternity dying. But the details of this final moment depend on physics that we do not yet fully understand. The black hole, as it shrinks, eventually reaches a size where quantum gravity effects become dominant. At that point, our current theories break down, and we do not know exactly what happens. Does the black hole vanish completely? Does it leave behind a tiny remnant? Does it explode? These questions remain open. After the last black holes evaporate, the universe will enter its final phase. No matter, no light, no structure. Just an ever-expanding void filled with a dilute bath of radiation and stray particles, all moving farther and farther apart. This is the heat death of the universe, the ultimate consequence of the second law of thermodynamics. It is a bleak vision of the far future, but it is also a beautiful one in its own way. The black holes, those children of gravity and space-time, will be the last sentinels of a universe that was once filled with stars and galaxies and life. They will be the final chapter of a story that began with the Big Bang. But we are not there yet, not by a long shot. We are living in the age of stars, in a universe that is young and vibrant and full of light. And we are learning, slowly but surely, to understand the dark objects that share this universe with us. Let us now take one more deep dive into the physics of black holes. Specifically, let us talk about the relationship between black holes and thermodynamics. In the early 1970s, a remarkable connection was discovered between the behavior of black holes and the laws of thermodynamics. The laws of thermodynamics, which govern how heat and energy flow in ordinary systems, turned out to have exact analogues in the physics of black holes. The first law of thermodynamics says that energy is conserved. The analogous law for black holes says that when a black hole changes, the change in its mass is related to the change in its area, its angulus, momentum, and its charge. The second law of thermodynamics says that entropy, a measure of disorder, always increases. The analogous law for black holes, known as the area theorem, says that the total area of all event horizons in the universe never decreases. In any process, the total event horizon area can only grow or stay the same. This analogy was initially thought to be just a mathematical coincidence. But then Jacob Bekenstein proposed that it was more than an analogy. He argued that the area of a black hole's event horizon is literally a measure of its entropy. A larger black hole has more entropy, just as a hotter gas has more entropy. And then Hawking showed that black holes have a temperature. The Hawking temperature, though incredibly tiny for astrophysical black holes, is real. It is proportional to the surface gravity of the black hole and inversely proportional to its mass. A small black hole is hot. A large black hole is cold. With these discoveries, the analogy between black holes and thermodynamics became an identity. Black holes are thermodynamic objects. They have entropy. They have temperature. They obey laws that are identical in form to the laws of thermodynamics. And this has profound implications. The entropy of a black hole is enormous. It is proportional to the area of the event horizon divided by the Planck area, where the Planck area is an incredibly tiny quantity, defined by the fundamental constants of nature. For a stellar mass black hole, the entropy works out to something like 10 to the power of 77. For a supermassive black hole, it is 10 to the power of 90 or more. These are the most entropic objects in the universe. In fact, it has been estimated that the total entropy of all the supermassive black holes in the observable universe accounts for the overwhelming majority of all the entropy in the cosmos. This tells us something profound. The entropy of the universe, the ultimate measure of its disorder and the arrow of time, is dominated by its black holes. In a very real sense, black holes are the universe's accounting system, keeping track of the flow of information and disorder on a cosmic scale. And yet, we still do not know exactly what the entropy of a black hole counts. In ordinary thermodynamics, entropy counts the number of microscopic arrangements that a system can have while looking the same on the large scale. For a gas in a box, entropy counts the number of ways the molecules can be arranged while maintaining the same temperature and pressure. For a black hole, the microscopic degrees of freedom are unknown. What are the tiny building blocks that make up the interior of a black hole? What are the microscopic states that give rise to the enormous entropy? These questions are at the heart of quantum gravity, and answering them would be a major breakthrough in our understanding of the universe. String theory has made some progress here. In certain special cases, string theorists have been able to count the microscopic states of black holes and reproduce the Bekenstein-Hawking entropy formula exactly. This is one of the great achievements of string theory and a strong hint that it is on the right track, even if a complete theory of quantum gravity remains elusive. Let us now explore a few more exotic and theoretical aspects of black holes before we begin our journey back to the present day. White holes. If a black hole is a region of space from which nothing can escape, a white hole is the time reverse. It is a region of space into which nothing can enter, but from which matter and energy can emerge. In the mathematics of general relativity, white holes are perfectly valid solutions to Einstein's equations. But there is a catch. While black holes form naturally from the collapse of matter, there is no known mechanism that can produce a white hole. White holes seem to violate the second law of thermodynamics because they would decrease the total entropy of the universe. For this reason, most physicists believe that white holes do not exist in nature, even if they are mathematically possible. However, some speculative theories of quantum gravity suggest that black holes might transition into white holes at the very end of their lives. The idea is that a black hole, after evaporating down to the Planck mass, might undergo a quantum bounce and briefly become a white hole, spewing out all the matter and information it had previously swallowed. This is a beautiful and speculative idea, and it remains very much on the frontier of theoretical physics. Naked singularities. In general relativity, a singularity is always hidden behind an event horizon. This is the content of the cosmic censorship hypothesis, proposed by Roger Penrose. The hypothesis states that nature never produces a singularity that is visible to the outside universe. Every singularity is clothed in an event horizon, hidden from view. But is this always true? Can there be situations where a singularity is not hidden, where it is exposed to the cosmos like an open wound in space-time? These hypothetical objects are called naked singularities, and their possible existence is one of the most debated topics in gravitational physics. If naked singularities exist, they would be places where the laws of physics break down in a way that is visible to the rest of the universe. Predictions would become impossible near a naked singularity, because the usual rules of cause and effect would no longer apply. It would be as if a piece of the universe had gone permanently unpredictable. Most physicists believe that cosmic censorship holds, at least in realistic physical situations. Computer simulations of collapsing matter generally produce event horizons that successfully hide the resulting singularities. But there are some theoretical scenarios involving highly symmetric or finely tuned initial conditions where naked singularities can form. Whether these scenarios have any relevance to the real universe is still an open question. Now, let us talk about something called the firewall paradox. This is one of the most recent and contentious debates in theoretical physics, and it centers on the event horizon of a black hole. The traditional picture, based on general relativity, says that the event horizon is a smooth boundary. Nothing special happens when you cross it. You do not feel anything. You do not see anything. It is just a mathematical surface that marks the point of no return. But in 2012, a group of physicists proposed that this picture might be wrong. They argued that if you take quantum mechanics seriously, the event horizon might actually be a wall of intense radiation, a firewall that would instantly destroy anything that tried to cross it. The argument is subtle and involves the interplay between quantum entanglement and the no-cloning theorem. The basic idea is that the information that escapes a black hole through Hawking radiation must be entangled with the information inside the black hole. But quantum mechanics limits the amount of entanglement that a system can have. If the Hawking radiation is maximally entangled with early radiation that has already escaped, it cannot also be entangled with the interior of the black hole. And without that entanglement, the smooth, empty space at the event horizon breaks down, replaced by a curtain of high-energy particles. The firewall paradox sparked a furious debate that is still ongoing. Some physicists accept the firewall argument and believe that event horizons really are violent places. Others think there is a flaw in the reasoning, or that the resolution involves a deeper understanding of quantum gravity that we have not yet achieved. Still others have proposed novel solutions, such as the idea that the interior of the black hole and the exterior are connected in subtle quantum mechanical ways that avoid the need for a firewall. Whatever the resolution turns out to be, the firewall paradox has been enormously productive. It has forced physicists to think more carefully about the nature of event horizons, the role of entanglement in gravity, and the relationship between information and space-time. It is a puzzle that may ultimately lead to a breakthrough in our understanding of quantum gravity. We are nearing the end of our journey now. We have traveled from the smallest black holes to the largest, from the oldest to the youngest, from the best understood to the most mysterious. We have explored how black holes form, how they live, how they feed, how they interact, and how they will eventually die. But before we conclude, let us step back and reflect on what black holes really mean for us. Here on this small planet orbiting an ordinary star in an ordinary galaxy. Black holes are the ultimate expression of gravity. They show us what happens when matter is compressed beyond all limits, when space-time itself is bent and broken. They are the places where the familiar concepts of space and time lose their meaning, where the laws of physics as we know them reach their breaking point. And yet, for all their strangeness, black holes are not alien to us. They are built from the same stuff we are. The atoms that make up a black hole were once part of stars, stars that shone for millions or billions of years, stars that may have had planets, stars that may have nurtured life. The black hole is the final chapter of a stellar story that began with the same cosmic ingredients that make up our world. When you look up at the night sky and see the band of the Milky Way stretching from horizon to horizon, you are looking at a galaxy that contains 100 million black holes or more. Some of them are ancient, formed when the universe was young. Some of them were born recently from the deaths of massive stars in our galactic neighborhood, and one of them, the one at the very center, has been shaping the destiny of our galaxy for billions of years. We cannot see them, but they are there, hidden in the dark, pulling on the fabric of space and time, bending light, swallowing stars, merging with each other in collisions that shake the very foundations of reality. They are the silent architects of the cosmos, and we are only now learning to read the blueprints they have drawn. The study of black holes is not just a branch of physics. It is a window into the deepest nature of reality. It is where gravity meets quantum mechanics, where information meets entropy, where time meets eternity. It is where we confront the limits of what we know and the vastness of what we do not. And that is perhaps the most beautiful thing about black holes. They are not just objects to be studied. They are questions to be asked. What is space? What is time? What is information? What is reality? We do not have all the answers yet, but we are asking the right questions. And every new observation, every new detection of gravitational waves, every new image of a black hole shadow brings us a little closer to understanding the deepest secrets of the universe. So the next time you find yourself lying under a dark sky, watching the stars slowly wheel overhead, take a moment to think about the invisible giants hiding among them, the stellar mass black holes, the supermassive engines, the wandering rogues, the ancient primordials. They are all out there, all around you, woven into the fabric of the cosmos like dark threads in a tapestry of light. And as you drift off to sleep, let this thought carry you into the darkness. The void is not empty. It is full of wonders. Every black hole is a story. Every event horizon is a door that we cannot open, but that we can learn to read from the outside. Every hawking photon is a whisper from the edge of eternity, telling us that even the darkest objects in the universe are not truly silent. They are speaking, and we are finally learning to listen. There is something poetic about the way black holes end their lives. After an eternity of silence, after an unfathomable span of time during which they slowly, imperceptibly shrink, they go out with a bang. The final evaporation of a black hole is not a gentle fading. It is an explosion. As the black hole gets smaller and hotter, its rate of radiation increases. In its final seconds, it reaches temperatures so extreme that it produces a burst of particles and energy, a last gasp of light in a universe that has long since gone dark. Some physicists have speculated that if we could observe such an event, it would be a spectacular fireworks display, a brief bloom of energy in the endless night. Others have wondered whether these final evaporation events might be detectable, even in the present universe, as mysterious bursts of high-energy radiation from the remnants of primordial black holes that have been shrinking since the beginning of time. Searches for these evaporation signatures are ongoing. So far, no definitive detection has been made, but the search continues, driven by the tantalizing possibility that the echoes of the first black holes in the universe might still be ringing across the cosmos. And what about micro black holes? These are black holes with masses far below that of any star, black holes that would be smaller than an atom. In theory, such tiny black holes could be produced by concentrating enough energy into a small enough space. Some physicists have speculated that high-energy particle colliders like the Large Hadron Collider at CERN might be able to produce micro-black holes. If certain theories about extra dimensions of space are correct, the idea of creating a black hole in a laboratory might sound terrifying, but there is no cause for alarm. A micro-black hole produced in a particle collider would evaporate almost instantly through Hawking radiation, lasting for only a fraction of a second before vanishing in a tiny puff of particles. It would pose no danger whatsoever. In fact, its detection would be one of the most important discoveries in the history of physics, because it would confirm the existence of Hawking radiation and possibly reveal extra dimensions of spacetime. So far, no micro black holes have been detected at the Large Hadron Collider or any other experiment, but the idea remains tantalizing, and future, more powerful colliders might have a better chance of producing and detecting these exotic objects. Let us also briefly discuss a concept that connects black holes to the very structure of information in the universe: the holographic principle. We touched on this earlier, but it deserves a deeper exploration. The holographic principle, inspired by the study of black holes, suggests that all the information in a three-dimensional volume of space can be encoded on a two-dimensional surface that surrounds it. The maximum amount of information that can fit inside any region of space is proportional not to the volume of that region, as you might naively expect, but to its surface area. This idea originated from the Bekenstein-Hawking entropy formula, which tells us that the entropy of a black hole, and therefore the amount of information it contains, is proportional to the area of its event horizon, not its volume. If the interior of a black hole contained more information than its surface area could encode, it would violate the laws of thermodynamics. The holographic principle has been extended beyond black holes to the entire universe. In some formulations, the entire three-dimensional universe we inhabit might be a projection of information encoded on a distant two-dimensional surface. It is a mind-bending idea, and while it remains speculative in its most extreme forms, it has found strong mathematical support in certain theoretical frameworks, particularly in the work of Juan Maldacena, who showed in 1997 that a theory of gravity in a particular kind of curved spacetime is exactly equivalent to a quantum theory without gravity on the boundary of that spacetime. This result, known as the ADS-CFT correspondence, has become one of the most important tools in theoretical physics. It provides a concrete example of how gravity and quantum mechanics can be unified, and it gives us a new way to think about the interior of black holes and the nature of spacetime itself. Now, as we wind down this journey, let us take a moment to appreciate just how far we have come in our understanding of black holes. 100 years ago, black holes were nothing more than a mathematical curiosity, a strange solution to Einstein's equations that most physicists, including Einstein himself, believed could not exist in nature. 50 years ago, we had found our first black hole candidates and were beginning to take them seriously. 20 years ago, we had accumulated strong evidence for their existence, but had never seen one directly. 10 years ago, we detected gravitational waves from merging black holes for the first time. And just a few years ago, we took the first photograph of a black hole's shadow. The pace of discovery is accelerating. With each passing year, we are finding new black holes, understanding them in new ways, and asking deeper questions about their nature. The next few decades promise to be the most exciting era in black hole research yet. Future. Gravitational wave observatories will detect millions of black hole mergers, giving us a detailed map of the black hole population across cosmic time. The James Webb Space Telescope and its successors will find supermassive black holes in the earliest galaxies, testing our theories of how the first black holes formed. New imaging techniques will allow us to make movies of gas swirling around black holes, watching matter fall into the void in real time. And advances in theoretical physics may finally give us a theory of quantum gravity that can tell us what lies inside a black hole. We are living in a remarkable time. The universe is opening up to us in ways that were unimaginable just a generation ago. And at the center of it all, quite literally, are the black holes. They have been there since the beginning. Primordial black holes may have formed in the first fraction of a second. Stellar mass black holes began to appear as the first massive stars lived and died. Supermassive black holes took their thrones at the centers of galaxies, growing and feeding and shaping the cosmos around them. Intermediate mass black holes emerged in the crowded hearts of star clusters. Rogues were flung into the void by the violence of supernovae and galactic mergers, and they will be there at the end, when the last stars have died, when the last planets have crumbled, when the universe is nothing but an endless, expanding darkness. The black holes will remain. Slowly, patiently, imperceptibly, they will radiate away their mass through Hawking radiation, each one a tiny beacon of warmth in an infinitely cold cosmos. And eventually, after spans of time that make the current age of the universe seem like the flutter of an eyelid, they too will be gone. But until that unimaginably distant day, they will continue to be the most fascinating, the most mysterious, and the most awe-inspiring objects in the universe. They are the void's many faces. They are the darkness that hides the light. They are the questions we have not yet answered. And they are the journey we are all on, whether we know it or not. Thank you for traveling with us tonight, across the universe, through billions of years of cosmic history, past the event horizons and the singularities, through the gravitational waves and the Hawking photons, to the very edge of what we know. If this journey moved you, if it made you think, if it made you wonder, then let us know in the comments below. Tell us which black hole fascinated you the most. And if you have not already, consider subscribing so you do not miss the next time we set sail into the cosmos. Until next time, keep looking up. The universe is full of wonders, and the darkness is just the beginning. But wait, before you close your eyes and drift away, there is still more to this story. We have covered the main families of black holes, but the universe has a few more surprises tucked into its darkest corners, and some of them are only now coming into focus. Let us go back to the idea of stellar mass black holes for a moment, because there is a mystery here that we have not yet explored. It is called the mass gap. For years, astronomers noticed something peculiar. When they catalogued the masses of known stellar mass black holes and neutron stars, there seemed to be a gap between them. Neutron stars topped out at about 2.5 solar masses, while the lightest known black holes started at about 5 solar masses. The region between 2.5 and 5 solar masses was empty. No objects seemed to live there. This was puzzling. If massive stars can produce remnants across a wide range of masses, why would there be a gap? Was there some physical process that prevented nature from creating compact objects in this range? Or were these objects just very hard to detect? Several explanations were proposed. One idea was that the supernova mechanism itself might be responsible. If the explosion that produces a compact remnant tends to either completely disrupt the star, leaving nothing, or leave behind a remnant that is either a neutron star or a black hole well above the gap, then the gap could be a natural consequence of the physics of stellar death. But then, in 2019, LIGO and Virgo detected a gravitational wave signal that challenged this picture. The event, called GW190814, involved the merger of a black hole of about 23 solar masses with a compact object of about 2.5 solar masses. This lighter object was right in the mass gap. Was it the heaviest neutron star ever found, or the lightest black hole? The signal alone could not tell us for certain, and the debate continues. And then there is the upper mass gap, a different kind of forbidden zone at the heavy end of the stellar mass black hole range. Stars with a certain range of core masses, roughly between about 65 and 130 solar masses, are expected to be completely destroyed by pair instability supernovae. In these explosions, the core of the star becomes so hot that photons begin to convert into pairs of electrons and their antimatter counterparts, positrons. This conversion removes radiation pressure from the core, causing it to collapse. The resulting thermonuclear explosion is so powerful that it obliterates the entire star, leaving no remnant at all. This means that stellar processes alone should not be able to produce black holes with masses in this pair instability gap. And yet, LIGO has detected at least one merger involving a black hole of about 85 solar masses, which sits right inside this gap. How did it get there? The leading explanation is that this black hole was itself the product of a previous merger. In a dense star cluster, where black holes are packed closely together, two smaller black holes could have merged to produce a larger one. This larger black hole could then have found another partner and merged again. This process of hierarchical merging could build up black holes of masses that would be impossible to produce from a single star. The detection of mass gap black holes through gravitational waves is opening a new chapter in our understanding of stellar evolution and black hole formation. It is showing us that the universe is more creative than we gave it credit for, finding ways to populate even the theoretically forbidden regions of the mass spectrum. Now, let us explore another dimension of the black hole story, their relationship with the fabric of space-time itself. Einstein's general relativity tells us that mass and energy curve spacetime, and that objects move along the curves of spacetime. Near a black hole, these curves become extreme. Spacetime is not just gently warped. It is twisted, stretched, and folded in ways that challenge our ability to visualize. One of the most dramatic effects is frame dragging, which we touched on earlier when discussing spinning black holes. A spinning black hole does not just curve spacetime. It drags it along, like a spoon stirring honey. This dragging effect extends well beyond the event horizon, influencing the orbits of stars and gas and the behavior of light in the surrounding region. Frame dragging has been confirmed experimentally, not near a black hole, but in the much weaker gravitational field of the Earth. NASA's Gravity Probe B mission, which orbited the Earth from 2004 to 2005, used ultra-precise gyroscopes to detect the tiny frame dragging effect of our planet's rotation. The effect was minuscule, just a few thousandths of a degree per year, but it was exactly what general relativity predicted. Near a spinning black hole, frame dragging is not minuscule. It is overwhelming. Space itself is rotating, and everything in the ergosphere is forced to rotate along with it. The energy stored in this rotation is enormous, and it is what powers the relativistic jets that stream outward from the poles of active supermassive black holes. The interplay between a spinning black hole and its accretion disk is one of the most complex and beautiful phenomena in astrophysics. The disk is warped by the frame dragging, precessing like a spinning top. That is slightly off balance. The magnetic fields are twisted and amplified. Turbulence and instabilities generate hotspots and flickering patterns in the emitted light. The James Webb Space Telescope has recently detected rapid flickering from the gas near Sagittarius A star, the supermassive black hole at our galaxy's center. These flickering signals change on timescales of minutes, which means they must originate from material very close to the event horizon, where orbital speeds are a significant fraction of the speed of light. By studying these rapid fluctuations, astronomers are learning about the chaotic, turbulent environment just outside the point of no return. Let us also take a moment to discuss something called a black hole binary in spiral in more detail, because it is one of the most beautiful processes in nature. Imagine two black holes, each several dozen times the mass of our Sun, locked in orbit around each other. They might have been orbiting for millions or even billions of years, slowly losing energy through the emission of gravitational waves. At first, the orbit is wide, and the gravitational wave emission is barely detectable. But as the black holes spiral closer, the emission intensifies. The final stage of the inspiral happens incredibly fast. In the last few minutes, the black holes close the remaining distance, their orbital frequency climbing rapidly. They go from orbiting each other every few seconds to orbiting hundreds of times per second. The gravitational wave signal sweeps upward in frequency, producing the characteristic chirp that LIGO detects. At the moment of merger, the two event horizons touch and fuse into one. The resulting black hole is initially distorted, bulging and rippling as it absorbs the energy of the collision. These ripples gradually die away as the black hole settles into its final shape, ringing like a struck bell. The frequency and decay rate of this ringing are determined entirely by the mass and spin of the final black hole, and they match the predictions of general relativity with astonishing precision. The energy released in a binary black hole merger is difficult to comprehend. The merger detected by LIGO in 2015 released about 3 solar masses worth of energy in the form of gravitational waves in less than a second. That is roughly 10 to the power of 47 joules. For comparison, the total energy output of all the stars in the observable universe is about 10 to the power of 48 watts. So for a brief fraction of a second, the merging black holes were radiating energy at a rate comparable to the combined output of every star in the visible cosmos. And this energy was carried not by light, but by ripples in the geometry of space-time itself. It is a fundamentally different kind of energy, invisible and intangible, passing through matter without leaving a trace except for the faintest vibration in the arms of a gravitational wave detector. The detection of gravitational waves has not only confirmed the existence of black hole mergers, but has also provided the most stringent tests of general relativity in extreme conditions. Every merger event is a laboratory experiment, testing whether Einstein's equations hold up in the strongest gravitational fields the universe can produce. So far, general relativity has passed every test with flying colors. But physicists continue to look for deviations, because finding one would be a clue to the long-sought theory of quantum gravity. Let us now consider something that brings the story of black holes full circle: the connection between the very first moments of the universe and the very last. In the beginning, the universe was hot, dense, and chaotic. Conditions were so extreme that primordial black holes might have formed spontaneously. At the end, in the incomprehensibly distant future, the universe will be cold, empty, and dark, with only black holes remaining as the last vestiges of the structured cosmos. Between these two extremes lies the history of the universe as we know it, the formation of the first stars, the ignition of the first galaxies, the growth of supermassive black holes, the evolution of cosmic structure, the emergence of planets, the appearance of life, and eventually, the slow decline of everything as the fuel of the cosmos is gradually exhausted. Black holes are present at every stage of this story, They are woven into the narrative of the universe from beginning to end. They are the architects and the inheritors, the builders and the destroyers, the questions and the answers. And here is one more thought to carry with you into the night. The boundary between a black hole and the rest of the universe, the event horizon, is not a wall. It is not a barrier. It is a horizon, just like the horizon you see when you look out across the ocean. The ocean does not end at the horizon. There is more beyond it. You just cannot see it from where you are standing. In the same way, the event horizon of a black hole is not the end. There is more beyond it. We just cannot see it from out here. And that is what makes black holes so compelling. They are not the end of the story. They are the boundary of what we can know, the edge of the map, the place where the familiar world fades into mystery. Every great civilization that has ever looked up at the stars has wondered about the darkness between them. What fills the space between the points of light? Is it truly empty? Or is there something there, something vast and powerful and hidden? We now know the answer. The darkness is not empty. It is full of black holes. Hundreds of millions of them in our galaxy alone. Trillions upon trillions across the observable universe. Some are the remnants of dead stars. Some are the engines that power galaxies. Some are wanderers, kicked out of their homes and drifting through the void. And some may be relics from the very birth of the cosmos, older than the first starlight. They are all out there right now as you listen to these words. The Milky Way is thick with them. Our neighborhood of the galaxy has its share. And one day, future generations of astronomers with more powerful telescopes and more sensitive detectors will map every one of them, creating a census of the invisible universe that lives alongside our own. But that is a story for another night. For now, let this journey settle into your mind like starlight settling into the ocean. Let the scale of it wash over you. From the tiniest primordial black hole, smaller than an atom, to the largest, supermassive monsters, bigger than our entire solar system. From the first fraction of a second after the Big Bang, to the last evaporation event in a universe grown cold and dark. Every one of them, from the smallest to the largest, from the first to the last, is a testament to the power of gravity and the strangeness of space-time. Every one of them is a puzzle. Every one of them is a wonder. And every one of them is a reminder that the universe is far stranger, far more beautiful, and far more mysterious than we could ever have imagined. Close your eyes now. Let the darkness come. And know that in that darkness, somewhere out among the stars, the void is watching back. Not with eyes, not with intention, but with gravity, with the silent, patient, eternal pull of the deepest mystery in the cosmos. Sleep well. The black holes will be there when you wake. Actually, before you close your eyes, there are a few more corners of this cosmic atlas that deserve our attention. We have journeyed far, but the universe of black holes still has a few chapters left to tell. Let us talk about a special kind of stellar mass black hole that forms not from a single collapsing star, but from the collision of two neutron stars. This is one of the most violent events in the cosmos, and it produces one of the rarest kinds of black holes. Neutron stars are the crushed remnants of massive stars that were not quite massive enough to form black holes directly. They are incredibly dense, with a mass comparable to the sun packed into a sphere about the size of a city. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. When two neutron stars orbit each other in a binary system, they slowly spiral inward, losing energy through gravitational wave emission. Over millions or billions of years, They get closer and closer until they finally collide. The merger is spectacular. A burst of gravitational waves is released. A jet of matter is ejected at near light speeds. And the heavy elements forged in the collision, gold, platinum, uranium, are scattered into space in what astronomers call a kilonova. But what is left behind? If the combined mass of the two neutron stars exceeds a certain threshold, roughly 2.5 to 3 solar masses, if you can't sleep, it's not because you're not tired. It's because your mind is still running, replaying the day, looping through the week, landing on something from years ago that has no business keeping you awake. Or you fall asleep fine and wake up at 3 a.m., wide awake. And now you're lying there doing the math on how many hours you have left before the alarm goes off. White noise doesn't fix that. Sleep playlists loop every few minutes and pull you back right when you were drifting. Meditation apps ask you to try. And trying is the problem. Your mind doesn't need to be quieted. It needs somewhere to go. Beyond the Stars is a full collection of long-form narrated space journeys built for a mind that won't stop on its own. Not music, not ambient noise. Calm, steady narration. Slow pacing. Deep space. Something your mind can follow without thinking. Something continuous enough that the looping just runs out of room. You're drifting through distant star systems, moving past quiet worlds, floating so far from everything that whatever was running in your head gradually loses its grip, without you forcing it. 5 overnight journeys, each one 6 to 8 hours long. No ads, no endings, no sudden sounds at 2 a.m. One purchase, any device, lifetime access. A sleep app costs you every single month, and it still interrupts you. This is $39 once, and it works while you sleep, not while you're trying to. If you're watching this channel, you already know what this kind of content does to a restless mind. Click the link below, get beyond the stars tonight, and actually sleep. The resulting object collapses directly into a black hole. This black hole is born not from the death of a single star, but from the marriage of 2 stellar corpses. It is a black hole built from the wreckage of worlds that already died once. In 2017, LIGO and Virgo detected the gravitational waves from a neutron star merger for the first time. The event, called GW170817, was accompanied by a burst of gamma rays, a kilonova visible in optical and infrared light, an emission across the electromagnetic spectrum, from radio waves to X-rays. It was the first time an astronomical event had been observed in both gravitational waves and light, opening a new era of multi-messenger astronomy. The remnant of that merger was likely a black hole of about 2.5 to 3 solar masses, making it one of the lightest black holes ever detected. These merger-born black holes occupy the very bottom of the stellar mass range, and they provide a unique window into the properties of matter at extreme densities. Now, there is another type of black hole environment that we should discuss. It is not a type of black hole per se, but rather a type of system that is essential to understanding how black holes grow and interact. These are called active galactic nuclei, and we touched on them earlier, but they come in many flavors. When a supermassive black hole at the center of a galaxy is actively consuming matter, it can produce a wide range of observable phenomena depending on the viewing angle, the rate of accretion, and the properties of the surrounding environment. Astronomers have historically given different names to these phenomena, creating a whole zoo of active galactic nuclei. Seifert, galaxies are spirals with bright, compact nuclei that show strong emission lines in their spectra. Type 1 Seyferts show both broad and narrow emission lines, indicating that we can see the fast-moving gas close to the black hole, as well as the slower-moving gas farther out. Type 2 Seyferts show only narrow emission lines, suggesting that our view of the inner region is blocked by a donut-shaped ring of gas and dust, called a torus. Quasars, as we discussed, are the most luminous active galactic nuclei, powered by supermassive black holes that are feeding at or near the maximum rate. They are most commonly found at great distances, meaning we see them as they were in the early universe. Radio galaxies are active galactic nuclei that produce powerful radio emission, usually from large-scale jets that extend far beyond the galaxy itself. These jets are among the largest structures in the universe, sometimes stretching for millions of light years. Blazars, which we also mentioned, are active galactic nuclei where the jet is pointed almost directly at us. Because of relativistic beaming effects, the jet appears much brighter than it would from any other angle. For a long time, astronomers were confused by the bewildering variety of active galactic nuclei. They seemed so different from each other that it was hard to believe they were related. But in the 1990s, a unifying model emerged. The idea was simple and elegant. All these different types of active galactic nuclei are basically the same thing: a supermassive black hole with an accretion disk and jets, viewed from different angles. If you look at the system from the side, the torus blocks your view of the inner region, and you see a Type 2 Seyfert, or a narrow line radio galaxy. If you look from a more face-on angle, you can see into the heart of the system, and you see a Type 1 Seyfert, or a quasar. And if you look directly down the jet, you see a blazar. This unified model of active galactic nuclei is one of the great achievements of extragalactic astronomy. It showed that the apparent diversity of these systems was largely an illusion caused by viewing geometry. The underlying engine, a feeding supermassive black hole, is the same in every case. Of course, the unified model is not the whole story. There are real differences between active galactic nuclei beyond just the viewing angle. Some black holes are spinning faster than others, which affects the efficiency of jet production. Some are feeding at higher rates than others, which affects the luminosity. Some are embedded in different galactic environments, which affects the supply of gas and the structure of the torus. But the basic framework of the unified model has held up remarkably well and continues to guide our understanding of these systems. Let us now talk about something that connects black holes to the very fabric of our existence: the heavy elements. We mentioned earlier that supernovae spread heavy elements into the cosmos, and that neutron star mergers produce gold and platinum. But the role of black holes in the production and distribution of heavy elements is even more profound than that. When a massive star collapses to form a black hole, the supernova that accompanies the collapse enriches the surrounding interstellar medium with a wide variety of elements. These elements are then mixed into the clouds of gas that will eventually form new stars and planets. Without these injections of heavy elements, the universe would be a very different place. There would be no rocky planets, no liquid water, no complex chemistry, and no life as we know it. Some of the heaviest elements in the periodic table, those beyond iron, are produced primarily through what is called the rapid neutron capture process, or R process. This process requires an environment with an extraordinarily high density of free neutrons, where atomic nuclei can capture neutrons faster than they can decay. For a long time, the site of the R process was uncertain. Supernovae were the leading candidate, but theoretical models struggled to produce the right conditions. Then came the neutron star merger, GW17 817 in 2017. The kilonova that followed the merger showed clear signatures of R-process elements, including strontium. This confirmed that neutron star mergers are a major, perhaps the dominant, source of R-process elements in the universe. And since many of these mergers produce black holes as their final product, the birth of a black hole is intimately connected to the creation of elements like gold, platinum, and uranium. Every gold atom in your ring, every platinum component in your electronics, may have been forged in the violence of a neutron star collision that ultimately created a black hole. The connection between the most destructive objects in the universe and the precious materials of our daily lives is one of the most beautiful ironies in all of nature. Now, before we truly bring this journey to a close, let us spend a few moments considering the philosophical implications of black holes. Black holes confront us with the limits of human knowledge. They are objects that are defined, in a fundamental sense, by what they hide. The interior of a black hole is the one place in the universe that is permanently and absolutely beyond our reach. No signal, no message, no information of any kind can escape from within the event horizon. Whatever happens inside is sealed away from the outside universe forever. This is a profound statement about the nature of knowledge. In science, we are accustomed to the idea that anything that exists can, in principle, be observed and studied. But black holes challenge this assumption. There are facts about the universe, facts about what happens inside event horizons, that are literally inaccessible to any observer outside. The universe keeps some secrets. And yet, even in the face of this limitation, we have learned an extraordinary amount by studying the effects of black holes on their surroundings, by detecting the gravitational waves they produce, by imaging the shadows they cast against the glowing gas around them. We have built a remarkably detailed picture of these invisible objects. We know their masses, their spins, their temperatures, their entropies. We know how they form, how they feed, how they merge, and how they will eventually die. This is a testament to the power of human curiosity and ingenuity. We have taken objects that are by definition invisible and turned them into some of the best studied objects in the universe. We have used the very limitations that black holes impose on us as clues to their nature, reading the universe like a detective reads a crime scene, piecing together the story from the evidence left behind. And the story is far from over. The next generation of telescopes and detectors will reveal things about black holes that we cannot even imagine today. New theories will replace old ones. New questions will replace old answers. And the black holes will continue to sit at the center of it all, dark and patient and full of secrets. There is a line from the poet Rainer Maria Rilke that captures something of the feeling we get when we contemplate black holes. He wrote about living the questions now, and perhaps gradually, without noticing, living along some distant day into the answers. That is what we are doing with black holes. We are living the questions, and with every new discovery, we are living a little closer to the answers. So as this journey comes to its end, let us hold on to that sense of wonder. Let us remember that the universe is not just a collection of facts to be catalogued. It is a mystery to be explored. And the black holes, with their infinite depths and their impenetrable veils, are the deepest part of that mystery. From the primordial specks born in the fire of creation, to the supermassive leviathans anchoring the great galaxies, from the stellar ghosts haunting the arms of the Milky Way, to the rogue wanderers sailing the emptiness between the stars, every black hole is a chapter in the longest and strangest story ever told. The story of the universe, the story of gravity, the story of space and time and the dance they do together at the edge of the abyss. And that story is still being written by the light of distant quasars, by the hum of gravitational waves, by the shadow of an event horizon against a glowing ring of fire, by the whispered radiation of a dying black hole in the cold and distant future. It is being written right now, and you are part of it. Good night. Dream of the void, and know that in its darkness there is beauty beyond measure. And yet there is one more thing, one more idea that deserves a place in this journey, because it is one of the most recent and most startling discoveries about black holes. For decades, we assumed that Hawking radiation was unique to black holes, that it required an event horizon, that specific boundary in space-time from which nothing can return. But new research from a team at Radboud University has challenged that assumption in a profound way. Their calculations suggest that Hawking radiation is not special to black holes at all. Any object with mass, any object that curves space-time, can produce a similar kind of radiation. The event horizon is not the essential ingredient. Gravity itself is. What this means is that everything in the universe, not just black holes, is slowly radiating away its mass. Stars, planets, moons, even the atoms in your body are emitting a Hawking-like radiation, losing energy particle by particle. Of course, for ordinary objects, the rate of this radiation is so impossibly slow that it has no practical effect. The timescale for a planet to evaporate through this process is something like 10 to the power of 90 years. That is a number so large that it makes even the lifespan of a supermassive black hole look brief. But the implication is stunning. Everything in the universe is temporary, not just stars and galaxies and black holes. Everything. Given enough time, the universe will not just go dark, it will dissolve. Particle by particle, photon by photon, every structured object will radiate away its energy and fade into the void. This is the ultimate conclusion of the physics that Stephen Hawking started when he first showed that black holes radiate. He opened a door that leads, in the end, to the evaporation of everything. The universe began with an explosion, and it will end with a whisper of particles escaping from objects that have forgotten they ever existed. But let us not end on a note of melancholy, because there is something deeply beautiful about this picture. It means that the universe is alive, not in the biological sense, but in the thermodynamic sense. Energy is flowing. Particles are being created. Information is being processed. Even in the coldest, darkest, most remote corners of the cosmos, something is happening. The quantum vacuum is fizzing with activity, producing particles from the curvature of space-time itself. The universe is not dead matter sitting in empty space. It is a living, breathing, dynamic system, constantly creating and destroying, building and dissolving, from the first instant to the last. And at the center of all this activity, both literally and figuratively, are the black holes. They are the ultimate expression of this cosmic process. They take in matter and energy and transform it, slowly, into Hawking radiation. They are the universe's recycling centers, taking the structured matter of stars and galaxies and breaking it down into its most basic components, spreading it back out into the void as thermal radiation. In a way, black holes are the universe's way of cleaning up after itself. They take the complexity and order of stellar systems and reduce it to simplicity and entropy. They are the great equalizers, the ultimate simplifiers. And when they finally evaporate, they leave behind nothing but a faint memory in the form of radiation. carrying the last whispered secrets of everything they ever consumed. It is a poetic and beautiful end, not with a bang, but with a slow, gentle, eternal exhalation of particles into the dark. So there you have it. Every type of black hole the universe has to offer, from the primordial specks that may have formed before the first star to the supermassive anchors of galaxies, from the stellar remnants that litter the arms of the Milky Way to the intermediate puzzles hiding in star clusters, from the spinning Kerr monsters dragging space around them to the rogue wanderers streaking through the void. We have explored their anatomy, their physics, their formation, their evolution, and their fate. We have touched on the deepest questions they raise about information, entropy, quantum gravity, and the nature of space-time itself. And we have barely scratched the surface. The universe of black holes is vast, and our understanding of it is growing every day. New telescopes are being built. New theories are being developed. New questions are being asked. And somewhere out there right now, a black hole is forming. A star is collapsing. A pair of stellar corpses is spiraling together. A supermassive engine is firing its jets across millions of light years. And a tiny primordial relic, older than starlight, is slowly, quietly, patiently fading away. The void has many faces, and tonight we have looked into all of them. Rest now. The cosmos will keep turning while you sleep. And when you wake, the stars will still be there, the galaxies will still be spinning, and the black holes will still be keeping their secrets in the dark spaces between the light. Until next time, sweet dreams among the stars, and one last thought to carry with you into that darkness between sleep and waking. The next time someone tells you that space is empty, remember this. Remember that between every star, in every galaxy, across every stretch of the cosmic web, there are black holes. Some are feeding, glowing with the fury of 1,000,000 suns. Some are sleeping, quiet and cold, waiting for a passing star or cloud of gas to drift too close. Some are falling toward each other, spiraling in an invisible dance that will end with a thunderclap of gravitational waves. And some are already gone, evaporated into nothing, their energy scattered across the cosmos like seeds in the wind. The universe is not empty. It never was. It is full of the most extraordinary objects ever imagined, objects that bend light and swallow time, and carry the secrets of creation locked behind horizons that no telescope will ever pierce. These are the black holes, the void's many faces, and they have been with us from the very beginning, silent companions on a journey through space and time that started with a bang and will end with a whisper. Every single one of them, from the smallest to the largest, is a window into the deepest truths about the cosmos we call home. And the view from that window is absolutely, utterly breathtaking beyond all possible human words. Now, rest. Let the weight of the cosmos settle gently on your shoulders. Let the gravity of these ideas pull you softly towards sleep. And know that out there, in the beautiful, terrifying, magnificent darkness, the universe is still telling its story, and you, right here, right now, are quietly listening. Good night.